Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Okay, homework for lecture 99. Number 1. In class we found that if L is equal to infinity, then E sub y is equal to 2k lambda over y times the sine of theta evaluated between 0 and pi over 2. Find the field for a finite line charge as shown on left, and then I give you a hint that we're going to evaluate E sub y equals 2k lambda over y times sine theta evaluated between 0 and theta prime. So the secret to answering this lies in evaluating what theta prime is. So let me just draw a picture. So we have number 1, and I'm going to have my line charge. We'll put it down here, and we'll have this be our 0, and we'll put our test charge point up here. This is a distance y, and this will be located at L, and this will be located at minus L. So you can see that this distance here is just L, this distance is y, this is theta prime. So what is theta prime? Well, who cares? We want to know what the sine of theta prime is, because that's in the expression that we have to actually evaluate. And so we can see from this drawing that the sine of theta prime is equal to L over the square root of y squared plus L squared. It's just the hypotenuse of this triangle. So then we evaluate this. We'd say that E sub y is equal to 2k lambda over y. Now the sine of theta prime is just going to be L over the square root of y squared plus L squared, minus sine of 0 is just 0, so that just doesn't contribute anything to our expression. So this is our final answer. E sub y is equal to 2k lambda L divided by y times the square root of y squared plus L squared. And if we wanted to, we could even pull out the L out of this and write this as 2k lambda over y times the square root of y squared over L squared plus 1. So I pulled out an L squared. When I pull it out of that square root, it just becomes L, and it cancels this L over here. And so we have this expression. And that'll set us up nicely for number 2. All right, problem number 2 asks, show that your answer from 1 reduces to the answer we got in class for L much, much greater than y. Okay? Well, that's why I wrote this expression this way, because now it just boils down to evaluating what happens to this square root sign if L is much, much greater than y. Well, if L is much, much greater than y, then the square root of y squared over L squared plus 1 is just going to be equal to y squared over L squared gets really big, so this basically causes this term to drop off to 0, and so we get this is just equal to 1, which means that E sub y is going to be equal to 2k lambda over gamma, 2k lambda over, not gamma, over y, which is, of course, what we got in class. Number 3, consider the opposite limit where y is much, much greater than lambda. What is the field then? Can you explain this? Well, let's have a look. So let's rewrite the expression that we got up here. And what I'm going to do is I'm going to divide things out differently than I did. So I'll start out with this expression that we had here. 2k lambda L over y times the square root of y squared plus L squared. And so now I want to focus on this square root again. I'm going to divide out a y. So this is going to give me 2k lambda L over, since I already had a y in the denominator, I'll get a y squared times the square root of 1 plus L squared over y squared. And of course, if y is much, much greater than L, then the square root of 1 plus L squared over y squared is going to be equal to 1. So that allows us to write that E sub y is then equal to 2k lambda L over y squared. So the total charge on the line then becomes, so what is the total charge on the line? Q will be equal to 2L, because it goes from minus L to L, times lambda, the charge density. And so if we take out this 2L lambda, right, then we can write E sub y is equal to KQ over y squared. So you see that it looks like a point charge with a charge of 2L lambda, which is kind of what we expect when we get very far away from it. Number 4, consider the electric dipole with dipole moment P equals Q times L in a uniform electric field, E equals E in the x direction. Consider and describe the net forces on the dipole. What happens? Okay, well, let's see. Let's draw a picture for this. Number 4. Here we've got a uniform electric field, which I'll kind of draw like this. Call it E. And this is in the x direction. And I'm going to put my dipole in here like this. It's of length L. And notice that it's making an angle of theta with respect to this field. So what's going to happen back here, if this is, say, the minus charge and this is the plus charge, well, back here, right, because it's a minus test charge, or a minus charge rather, there's going to be a force, we'll call it sub minus, a force in the minus x direction. But up here on the positive charge, actually it's the other way around, isn't it? Let's call this the positive charge and this the negative charge. I got the forces backwards. There's a force going on the positive charge going to the left or in the minus x direction, and on the negative charge it's being attracted towards, in the direction of the field line. So here we're going to have a force which is in the positive direction. This of course is going to cause a twisting motion or a torque. The sum of the forces, of course, is 0 because they're equal and opposite. The field is uniform, the charges are the same, just oppositely charged, so the sum of the forces is 0. But the sum of the torques, on the other hand, is not 0, right? And so what's the torque going to be? Well, it's the vector L crossed with F for either of these charges, right? Where L is now acting as like the lever arm, if you want to think of it that way. And so that would be Q times L cross E, still need that in there, which is equal to P cross E. So you see that the torque aligns the dipole in the direction of the field. Oh, yeah, I totally messed that up. Yeah, this should have been minus Q here. So this is the minus, and this would be the plus Q here. So we call this F minus. Yes, because the electric field starts at positive charges and ends on negative charges. So that means that it would be like there's a negative charge over here, which means the negative charge is going to be repelled from it or attracted to the other side, the positive charge side. And over here, it's the opposite. So it'll be attracted towards the negative charges that you can think of as being over here, creating this uniform field. It happens. All right, number 5, consider a nonpolar molecule in a non-uniform electric field at point P. What happens? Kind of an open question, but we can describe it fairly simply. So here's my charge. I'll make it positive. And of course we've got our field lines running every which way, radially outward. So let's just pick. So if I put a molecule, a nonpolar molecule, in this field, what's going to happen is that the molecule is going to stretch out. The positive charge, of course, is going to be as far as it can be from this positive charge here, whereas the negative charge will be closer to it. So it does the same kind of polarization that we've talked about in class. However, this is not a uniform field, which means that the force here on the negative charge, we'll call it F minus, is going to be greater than the force on the positive charge, which we'll call F plus. So if F minus is greater than F plus, then there's a net force, right? So the net force is not equal to 0, which means that it's going to accelerate, and it's going to accelerate in the direction of the charge. And that is pretty much what I was looking for there.